So now again, what was Planck trying to do? He was trying to find the expression for energy. So what was his approach? He divided the whole spectral range into small intervals d nu, meaning the entire frequency range. He divided into small intervals d nu. Let's say my frequency range was from 100 Hz to 500 Hz, which is a very toy example. The actual range would be spanning over thousands of Hertz, but just for your understanding, let's say I'm working at a range between 100 to 500 Hertz. He divided it into small strips of d nu, let's say 5 Hertz each. So he's creating small intervals 100 to 105, 105 to 110, and so on up to 495 to 500. So the entire range which he has, he's dividing it into small strips. And then what he's trying to do, find out the number of oscillators vibrating within this frequency range. And by oscillator we mean atom. So how many atoms exist within this frequency range, and he wants to find out the average energy of one atom. So if I take the energy per atom and multiply it by the number of total atoms, we get the total energy, right? So this was his approach. So we're now going to actually delve into the derivation for energy per oscillator and what Planck did with this approach and this idea. So again, for context, what is he trying to do? He is trying to find out the energy, average energy per atom. This is what he is trying to find out. His assumptions are that each atom receives heat energy and oscillates. That oscillation is what causes radiation, and this energy is discrete. So with these assumptions, and then he took the entire frequency spectrum, divided it into small strips for convenience in calculation. His idea was, I'll find the total number of atoms in this range, I'll find the average energy per atom, and then I'll multiply it, I'll get an expression for my total energy. This is what he wanted to do. So there are two parts to it, like we just saw, total number of atoms and average energy per atom. Atom and oscillator are the same in this context. So we'll start by looking at the average energy per oscillator, then we'll go on to total number of atoms. So to calculate the average energy per oscillator, Planck used a theory given by this person called Boltzmann. So what did Boltzmann say? The number of oscillators in the ith level is given by n0 e raised to minus ei by kt, where ni is the number of atoms or oscillators present in the ith energy level, n0 is the number of atoms or oscillators present in the 0th level, that is the ground state, e raised to power minus ei. Ei is the energy of the ith energy level, k is the Boltzmann constant, and T is the temperature. So this was the formula given by Boltzmann, and Planck started with this formula to derive his expression. So using this formula, n1 is n0 e raised to power minus e1 by kt, which is n0 e raised to power minus h nu by kt, where energy is simply h nu. And for the purposes of our calculation, for time being, we will denote h nu by epsilon. It is just another notation, because every time you need to keep writing h nu, instead we will give epsilon, and then finally when you get your final expression, we will replace epsilon by h nu again. So n1 is n0 e raised to power minus e1 by kt, where e1 is nothing but h nu and h nu is nothing but epsilon. n2 is n0 e raised to power minus e2 by kt, e2 is 2 h nu, which is 2 epsilon, e3 will be 3 h nu, which is 3 epsilon, and so on. So now we have the expression for the number of atoms in each individual level. So to find the total number of atoms or oscillators, obviously we are going to sum everything up, n0 plus n1 plus n2, so on, which is n0 plus n0 e raised to minus epsilon by kt plus n0 e raised to power minus 2 epsilon by kt minus 3 epsilon, and so on. It goes infinitely because the number of energy levels is infinite. So what we do, we take n0 out as a common term, we get n0 into 1 plus this entire term. We've simply taken this expression and taken n0 out common. Now if you look carefully at this expression, you will notice that it is of the form 1 plus x squared plus x cube. It is of that pattern, and when you have an infinite series of this pattern, it is equal to 1 by 1 minus x. So Basically, what does this expression give us? N naught divided by 1 minus x, where x is equal to e raised to minus epsilon by kt. Again, how did we get this? We had the expression for each individual level, we added everything, we took n naught out because it's a common factor, and then this term, it resembles this sequence 1 plus x square plus x cube. And we know from mathematical proofs that this, when you have an infinite series of this pattern, it is equal to 1 by 1 minus x. So you get n naught by 1 minus x, where x here represents e raised to minus epsilon by kt. This is what we've derived so far.